Welcome to all of you. In this lecture, we are going to discuss about the derivation for the order of Butterworth filter. Let us first go through the parameters. Omega p pass band frequency in radians per second, omega r stop band frequency in radians per second, then k1 the pass band attenuation and the k2 the stop band attenuation. So the Butterworth filter transfer function is represented by h of s is equal to 1 divided by 1 plus omega divided by omega c to the power of 2n whole to the power of 1 by 2. Let us call this as the expression 1. Now applying log magnitude squared response or 20 log base 10 on both sides of equation 1, we get 20 log base 10 of h of s is equal to 20 log base 10 of 1 divided by 1 plus omega divided by omega c to the power of 2n whole to the power of 1 by 2. On the left hand side, we now call it as the 20 log base 10 of h of s as h of s modulus dB, that will be equal to. Now take this denominator part to the numerator, the power will become negative. As per the laws of the logarithm, we can take out this power outside, and by making simplification, we obtain minus 10 log base 10 of 1 plus omega divided by omega c to the power of 2n. Let us call this as the equation 2. Now let us consider the stop band specification and then apply that to the equation 2. That is, in place of omega, omega r, in place of h of s in terms of dB, make use of the k2. Now doing that, we get k2 is equal to minus 10 log base 10 1 plus omega r divided by omega c to the power of 2n. Perform the cross multiplication of this minus 10 to the left hand side, we obtain this expression. Then apply antilog on both sides. We get 10 to the power of minus k2 by 10 is equal to 1 plus omega r divided by omega c to the power of 2n. Take this one to the left hand side. We get 10 to the power of minus k2 by 10 minus 1 is equal to omega r divided by omega c to the power of 2n. Let us call this as the equation 3. Now in the equation 2, now make use of the passband specifications, that is omega p and the k1. The simplification procedure is same as what we have done over here. Therefore, follow the same procedure here also with respect to passband specification. After final simplification, we obtain 10 to the power of minus k1 by 10 minus 1 is equal to omega p divided by omega c to the power of 2n. Call this as equation 4. Now make use of the equation 3 as well as the equation 4 to obtain the expression for the order of the filter. That is equation 4 divided by equation 3 we are making. So on the left hand side, so the numerator belongs to equation 4, denominator belongs to equation 3. Similarly on the right hand side. And on the right hand side, omega c is a common factor in both of this. Therefore, this omega c once divides and the remaining is being written over here. Now apply logarithm on both sides, log to base 10. So after applying log to base 10, this is what we are going to obtain. And in this part, as per the laws of the logarithm, we can take out this 2n and we can write over here. That has been done and represented here. Now at this stage, we are able to obtain the expression for order of the filter n. So keep the n here itself and everything else perform a cross multiplication. By doing that, we obtain the order of the filter as n is equal to log 2 base 10, 10 to the power of minus k1 by 10 minus 1 divided by 10 to the power of minus k2 by 10 minus 1 whole divided by 2 log base 10 omega p divided by omega r. So this is the expression for the order of the filter. Always remember, while making the calculation, if the order is obtained as a fractional value, always round it off to the next integer value only. So now we can also calculate the cutoff frequency omega c. We are going to make use of the equation 3 and the equation 4 from the derivation of the order of the filter. Making use of them, we are calculating the omega c. We are going to calculate this cutoff frequency with respect to pass band specification, with respect to stop band specification, as well as a compromise between these two. Now let us first start with pass band specification. So we are going to make use of the equation 4 directly over here. So we need to have an expression for omega c. Therefore, now what we are going to do is the power 2n, we are trying to take it to the left side. By doing that, we get the expression 10 to the power of minus k1 by 10 minus 1 to the power 1 by 2n is equal to omega p divided by omega c. Now we can obtain expression for omega c. At this stage, since we are doing with respect to the pass band, omega c we call it as omega c1. Omega c we consider it as omega c1, and its expression will be omega p divided by 10 to the power of minus k1 by 10 minus 1 whole to the power of 1 by 2n. So a similar procedure is also being done for the stop band. So expression 3 from the derivation of the order of Butterworth filter is being considered here, and the similar procedure what we done previously for pass band, same has been done, and here we call this as the omega c2. That means with respect to stop band specification, the cutoff frequency, we call that as omega c2 given by omega r divided by 10 to the power of minus k2 by 10 minus 1 whole to the power of 1 divided by 2n. Now an average of pass band and stop band, that's a compromise between these two, is omega c, that is equal to omega c1 plus omega c2 divided by 2. So while making the calculation, if the final result is required with respect to the pass band specification, then we can make use of omega c1 as the cutoff frequency. So in the calculation, if you require the stop band specification in the final result, then we can make use of omega c2 as the cutoff frequency. Or if you want to have a compromise between the pass band and the stop band, then we can take an average of them, and then we can make use of this omega c. Thanks for joining.